Alright, so today we're going to do a real quick Billy Mays style demo on running a hydraulic model in the cloud. In this case, we're going to be running HEC-RAS in the AWS cloud, Amazon Web Services. So why is this helpful? Traditionally, you would run your model simulations sequentially in a desktop program on a single Windows PC. So if model runtimes are 12 hours for a large watershed simulation over a multiple day historical storm, if you need to run 12 different versions of this model, you would only be able to compute one at a time. Further, if you're running these on your working computer, they will basically brick your machine with CPU usage at 100% in the case of HEC-RAS, or if you're using a GPU solver from another model, it'll take your GPU to 100%. And so it's not practical to do other compute intensive work throughout the day if you're also running simulations. So generally what we would do is build the model or complete whatever work throughout our workday, and then overnight run a single 12-hour simulation. And that works well if you only need one simulation in a day, but if, for example, you need to perform sensitivity analysis with 10 separate runs on 3 separate parameters, that could take an entire month if you're running one simulation overnight. So how do we mitigate this issue? For our team, what we ultimately went with was a solution that leveraged a local compute cluster of Windows desktop machines. But for a team without access to an on-prem compute cluster, and especially if the workflow is uneven, where you will need to compute a large volume of runs in batch, in some seasons and none in others, a cloud workflow may be the best option. And so by scaling up using cloud and virtual machines, we can parallelize our runs to complete an arbitrary number of simulations within the same duration that it takes to complete one, and further offloading this to external hardware. So for an example where runtimes are 8 hours long and we need to compute 30 simulations for our sensitivity analysis, we could actually start the simulation at the beginning of the day, and we would have an answer by the end of our workday, since it could complete 30 simulations using external cloud compute. Now, I'm hoping that this video will be useful for anyone who's new to setting up cloud infrastructure. Before I had built out this workflow, what I found was that there's no shortage of technical documentation on any specific aspect of AWS or any other cloud provider. But there really seems to be a lack of documentation on best practices for setting up a particular automation workflow. In this case, running simulations statelessly in a scalable way on the cloud. So I'd like to show a high-level overview of a general workflow that I found to be effective. So hopefully this will be a good reference point or basic recipe for your own cloud-based simulation workflows. So for those familiar with HEC-RAS, if you use this model engine, on a day-to-day basis, you're likely to be working in Windows. That's where the graphical user interface is compiled for. But there are also some binaries compiled for Linux. So in this case, we're going to go ahead and use a Linux distribution on the cloud rather than Windows just to run the model because Linux VMs are pennies on the dollar compared to Windows. So what this script is doing is actually forking our model into 4 separate versions. This is useful for sensitivity analysis, calibration, especially if you want to dial in one parameter. In our case, just for this demo, we are just changing the simulation time of this plan to 4 different durations. So this is the dashboard here for AWS EC2 instances, which basically lets you view and manage virtual machines or VM instances in the AWS cloud. And so this whole process we're going to demo is done through Python, but we can at least view what's going on by checking this dashboard. We're going to go ahead and run this demo Python script here. And so this first part, you see the Windows desktop software popping up here. What it needs to do is run a certain part of the Windows preprocessor before sending it out to Linux. For whatever reason, there's a small piece of the preprocessor that did not get compiled to Linux by the core, and we don't have access to the underlying source of this model engine to be able to compile it ourselves. And so what we need to do is actually run this Windows preprocessor before sending our project up to the cloud to run in Linux. So it's a little bit hacky, but it needs to asynchronously run the desktop software on one thread and then run another process which can monitor and stop it prematurely on another thread in order to make sure that it finishes that piece that it needs in the Windows preprocessor before sending it up to the cloud. And so as you can see, it says uploading files. So that is using a S3 bucket, which is the AWS cloud storage solution. And so these virtual machine instances that you launch through AWS EC2, they have access to this storage on the cloud. And so in order to make this happen statelessly, abstract the HEC-RAS solver to a cloud service in order to be able to make this scalable. And right now in this demo, we're creating 4 instances to run 4 versions of our model in parallel at the same time in the cloud. We want to be able to scale this up where we could launch 100 or 1,000 if we wanted to and we had the budget to do that. And so each of these virtual machines gets created upon launch. And so we have a copy of the HEC-RAS Linux solvers and other dependency binaries on S3, which actually get pushed to each instance as it starts up. And our Python script here simply launches the instances and gives them enough specification so that they can handle themselves once they're in the cloud, which allows the process to happen statelessly. So we can see that the instances have all started up. They're currently running. Okay, it looks like the first one has terminated, which means that it's followed its instructions to start the model, pull the results back to the same shared S3 storage bucket, and then shut itself down and actually delete itself so that we don't have any extra resources idling and continuing to cost money in the cloud. So we can see that the results are there. So there's 3 files in here. A text file called progress with the simulation index, and this is just the standard out of this VM along its lifetime. So here we can see the output from the model as it runs. The Linux output is a little bit less verbose than the Windows for some reason. And then two other files which contain the results of the simulation. So it looks like all four have finished their mission. We can see that the results are there in the S3 bucket. So we'll go ahead and take a look at this i3 run. So the results are in there. Finished without errors. And we'll go ahead and download the two results files that it produced. And so, in a regular workflow, what we would do here is simply extract whatever useful information we need from these, be that metrics computed for a sensitivity analysis, suite of runs, or what we could actually do is serve these results from a web map hosted on the AWS cloud on a separate instance. So, and the trick here is that S3 storage is cheap, but to pull it down from the cloud is expensive, especially as these HEC-RAS results files get large. These can be a few gigabytes for a standard like watershed study size results file, which can get expensive if you're pulling down 20, 40 gigs of data for every time you run a sensitivity analysis or something. And so that's how the Amazon pricing kind of gets you to stay in the cloud, is they make it more convenient to process your simulation results, or do what you need with the data you've created, store it and use it all within their same cloud service. They just make that the most economic way to handle it. But in this case, we'll go ahead and just pull the results down locally. So we're just going to download it manually through this portal here. And then go ahead and pull that into our original HEC-RAS project. And opening the HEC-RAS software, we can see we have our results here. And yeah, so these are inundation depth results computed in Linux on the cloud in parallel as a stateless service.